Okay, well, so just give me a minute. Yeah, just a minute.
Sir, it was showing the quiz was not accepting answers.
Yes. Okay, so welcome back. Do you hear? Am I audible?
Excuse me, sir.
Yeah.
Sir,
Yeah.
it was when I submitted, it was showing the quiz was not taking answers any longer.
Yeah, because you are late probably to. I just
Okay, sir.
closed maybe because of that reason. Yeah.
Okay, sir.
Okay. So here we will continue with this the concept of complex functions with continuity and the differentiability of complex functions, right? So just to recall again, we have gone through already the limit. So if fz as z approaches to z naught, the limit is w naught. And if the difference between this fz and w naught can be made arbitrarily small by choosing z close to z naught, that was the idea. And then this delta epsilon definition also, we got the idea that whenever this difference, the absolute value less than epsilon, whenever z is from this delta neighborhood. Well, so the continuity again, because once you have the limit, the continuity follows. So a function fz is said to be continuous at z equal to z0 if you have this limit fz z equal to z tends to z naught w naught. If the limit fz exists and fz is defined at z naught, that is fz naught exist. Yeah, so what, there are two things. One is the limit, right? So the limit should exist. The limit fz as z approaches to 0 is w naught. The second is fz should also be defined at z naught, because in the limit, if you remember, that function this fz may not be defined at z naught, still we can talk about the limit. The function may not be defined at that point, but when we talk about continuity, fz naught should also exist, then only we call about, we can discuss about continuity. And then this fz naught, the function value at z naught should be equal to that limit of that fz, and then we call that function is continuous. So again, exactly the same definition what we have for real functions, the real valued functions. So a function fz ux plus I v xy is continuous at the point z naught equal to x naught plus iy naught if and only if the function uxy and vxy are continuous at x naught y naught, right? A function is said to be continuous if these two functions, the uxy and vxy, as discussed before, they are continuous. So this limit exists, but it's not equal to fz naught. Yeah, there might be a situation that the limit exists, fz naught also exists, but they are not equal. In that case, we call that removable discontinuity. Yeah, the same terminology we have also used earlier. This is called removable discontinuity. Why removable? Because if you redefine your function, that my fz naught at that point, I redefine my function. If I redefine my function, then this function will become continuous. So for instance, we have here the continuity of fz. We want to discuss where fz is given by this function. When z is equal to 2i, the function not equal to 2i function is given by this quotient. When z is equal to 2i, function is given as minus 10i. So we will check the limit as z approaches to 2i, because we want to get that continuity as z approaching to 2i. So the limit as z approaching to 2i of this function I z cube minus 8 over z minus 2i. So z cube minus 8, here just we have written this I4, which is 1, and then z minus 2i, just rephrase it. And I we have taken common, so z cube minus 8i over z minus 2i, which can be factorized again, and then this factor will get cancelled, and when you put this z is equal to 2i, you will get minus 12i. So here it was minus 10i, but this limit is 12i, so the function is not continuous, and in this type of discontinuity we call that indeed that which we are talking about before, removable discontinuity. Because if we redefine our function, if we say that at z is equal to 2i the function will take this value, then the function will become continuous. So we can easily make that function continuous by redefining the function value at z is equal to 2i. Okay. So the differentiability, yeah, so the most important now the concept where you really need to focus is the differentiability, which will follow which will be followed by the discussion on analyticity. Actually that is the main topic of this complex variable, because that analyticity is very important when we have the integral, the complex integrals, and many other series expansion and so on. Everywhere that analyticity will be discussed, which is slightly different from the differentiability. So a function fz is said to be differentiable at a point z naught in C if this fz naught plus delta z minus fz naught over delta z exist independent of the path in which delta z approaches to 0. Right, the similar definition what we have always for the differentiability, the function is said to be differentiable at a point when this quotient here f z naught, you varied that z naught, so f z naught plus delta z minus f z naught over delta z, and then the limiting situation, that limit delta z goes to 0, exist independent of the path, exists itself is independent of the path, otherwise you will not call that exists, that depends on the path. So in fact this is just to highlight a bit, but it has no meaning. So if this limit exists in which this delta z approaches to 0, then we call that value as f prime z naught, right? It is denoted by f prime z naught, and it's called the derivative of f at z naught. Yeah, so nothing new. It's a like one variable calculus you have learned, that fx plus delta x minus this fx or fx naught if you are talking about delta x, and then the limit delta x goes to 0. Yeah, that was one variable. But now we have that complex variable where again just remember, in the complex variable, in the one variable you had the two paths, one from the right hand side, one from the left hand side. But now again in the complex case you have infinitely many paths, like in two variable calculus. So the same problem. So
Sir, why did you cancel out that independent of path part while explaining
yeah,
that part? I didn't
the point
understand.
is, I said that is obvious. When we call that limit exists, that means
Yes.
itself that it should be independent of path, right?
Yes, sir. Yes, sir.
So if the limit depends on path, along different paths we have different value, we will not call actually that limit exists, right?
Exists. Yes, sir.
Yeah. So
Yes.
therefore it is actually not needed. The
Okay.
existence is fine. Okay, so fz is equal to z square, for instance, and you want to get f prime z from the basic definition. So you have f z plus delta z minus f z over delta z, and then z plus delta z square and minus this z square over delta z, and z square delta z square 2z delta z minus z square over delta z. That is you can just expand this simply, then the z square will get cancelled, one delta z will also get cancelled, and as delta z approaches to 0 you will get a value as 2z. So the derivative of this like z square is 2z. So all those actually what we have learned before, all those many of them will directly be translated for here also for differentiability. So like z square you have seen 2z. So it's like x square is 2x. But there are several other cases which need more attention. So for instance here fz is equal to z, this conjugate is not differentiable at any point, is not differentiable at any point, that we will see. Because when you consider this quotient here, that means this z plus delta z, this conjugate minus z conjugate over delta z, then what you have here, limit delta z to 0, delta z over delta z, and if this delta z approaches to 0 along the real axis, right, what will happen, what will be the limit if this delta z approaches to 0 along the real axis? Then we have to see that what is that limit. That means we are fixing a path, so along this path what will be that limit? Can you tell me?
1.
That will be 1.
1.
Okay. So that is 1, and along imaginary axis?
-1.
-1, yes. So that means that limit does not exist. True? That limit does not exist because along two different paths you have two different values, so the limit does not exist. And so that's what you just remember this, that this z conjugate is not differentiable for any point, right? Any point. We have not fixed the point also, right? If you take any point, the same situation along this x-axis you approached and then along y-axis you approach, you will have a different situation. Correct?
Yes.
Excuse me, sir.
Yeah.
Sir, here can we take delta z as delta x plus iota delta y?
Yes. Yes. Delta z is like delta x plus I delta y.
Okay, sir.
So you have the differentiability implies continuity here also. So fz is differentiable at z naught, and then f is continuous at z naught. So the differentiability implies continuity in this case. So we can prove it actually. So for instance, you take this difference fz naught plus delta z minus fz naught, and this is equal to fz naught plus delta z minus fz naught over delta z. Delta z you multiply it and you divide, and then you have here delta z not equal to 0. Yeah, so some delta z which is not equal to 0 you can multiply and divide. Then you take that limit delta z approaches to 0, so you have this limit here. And remember now that if the function is differentiable, we want to show that differentiability implies continuity, right? So if the function is differentiable, this limit will exist. So this limit will exist, and then you have the limit delta z approaching to 0, and this exists. So that means f prime z naught into 0, that is 0. So this limit is equal to 0, and that gives you that limit fz naught plus delta z is equal to fz naught. So we have that continuity. So the differentiability implies continuity. So we assumed here that differentiability, and that implies now the continuity, that limit fz plus delta z when delta z approaches to 0 is equal to fz naught. Analytic functions, which is just in continuation with this differentiability. So if the derivative f prime z exists at all points z naught of a domain D, then fz is said to be analytic in D. Just try to understand this. Here you will not see any difference now. So if the derivative f prime z exists at all points z of a domain, then fz is said to be analytic. So you have some domain here, some open, domain means always open. So I will not repeat that. It's always, so that some domain is there where the boundary is not included. So never in the domain you will not include the boundary. That is convention. So we have a domain here, and suppose this f prime z, I mean f prime z exists everywhere in this whole domain at any point of this domain. Then fz is said to be analytic in D. There is no difference basically whether you call analytic or you call that differentiable. Where the difference comes? So for analytic, the term regular and the holomorphic are also used. So that is okay. A function.
Excuse me.
Yes.
Sir, in first semester we have told that analytic function is the function for which we can write a Taylor expansion.
Yeah, we'll get to that also in complex setting as well. We have
Your voice was getting broken up when he was speaking.
Yeah, so here in the complex functions also that notion will be there, but little later. So first we go through these analytic functions. What are analytic functions? And then what is its connection with the Taylor series? That will follow. Yeah. So you will see if the function is analytic, you have a Taylor series. So that little later. Yeah. So we'll come to that point. So fz is said to be analytic. Now you focus here. Yeah. So what is the difference? This is a very critical point now. A function fz is said to be analytic at a point. Yeah, I'm talking about at a point now. At a point z0. If there exists a neighborhood of that point at all points of which f prime z exists. Did you get my point? There was no difference when I was talking about a domain, then f prime exists at all point in the domain, then I said fz is analytic in D. So fz is analytic in D or fz is differentiable in D, the meaning was same there. Because of that domain which was open, so there was no boundary at any point you can draw. What is the difference in open and close? When you have open domains, for example, this is open domain. At any point you take, you can have a small neighborhood. Any point in the domain you can take a neighborhood. At any point in the domain you can take a neighborhood. That is the beauty of that openness. So when we have a differentiability at all points, that means that the function was also differentiable in the neighborhood of that point, right? Because there is a neighborhood which lies again in D, and in D at all point the function is differentiable. So therefore that analyticity was obvious and was equivalent to differentiability when we were talking about a domain. But the actual difference is here. A function is said to be analytic. So for analyticity, you need little more than differentiability. So the function is not just differentiable at f at z0, but there should be a neighborhood where the function is differentiable. So the function may be differentiable at this z0, but may not be analytic. For analyticity, there should be a small neighborhood, however small does not matter, but there should exist a neighborhood where the function is differentiable. Then we call that the function is analytic at that point z0. Is that clear, the difference between the two? Is that clear?
Yes, sir.
Okay.
Excuse me, sir. If first statement holds, then second will automatically hold now. Why we need to mention?
See, the first was when we are calling about a domain. Yeah, we are discussing over a domain. I have a domain D. Then if the function is differentiable at any point in this, the function is also different analytic in that domain D. Clear? Now I am talking about a point, that how the analyticity is defined at a point.
Okay, sir.
Yeah, maybe in the example you will see the difference between the two. Huh? So here at a point it is defined as, I mean, this is more important to my opinion. You remember this definition because that will follow anyway that. So if we have defined our analyticity, that there should be always a point in the neighborhood of where the function is differentiable. So if this is the case, naturally this will follow the domain, yeah, because domain is open and at any point you have a neighborhood where the function is differentiable, therefore analytic. So analyticity and differentiability will be same when we are talking about domain. But when we are talking about a point, then the function may not be differentiable. The function may be differentiable at z0, but may not be analytic. So analyticity is little more than differentiability. There are some help regarding how to check the analyticity or in fact differentiability also. These are called Cauchy-Riemann equations. So these equations are very useful for checking the analyticity or the differentiability of a function. So if fz is equal to u plus iv be a function of the complex variable z, the partial differential equations del u over del x, del v over del y, or del u over del y and del v over del x are called Cauchy-Riemann equations. These are called Cauchy-Riemann equations. How these equations are coming, what is the relation with the differentiability, analyticity and all, we will also discuss that. So a function fz, is given, then these equations, so partial derivative of u with respect to x, if it is equal to the partial derivative of v with respect to y, and the second relation, these are called Cauchy-Riemann equations. So at this moment only this one, we will see how these Cauchy-Riemann equations are related to the
Sir, when del u upon del x is equal to del v upon del y, then we call it Cauchy-Riemann equation. Otherwise, we don't call it.
These are called Cauchy-Riemann equations. Whether they are satisfied or not satisfied, that is a different point, right? But these equations are called CR equations. The equations are fixed. These are CR equations. Whether they are satisfied for a particular function or they are not satisfied, that is a different matter. Correct? Yeah, so these are CR equations. Now, necessary and sufficient conditions for analyticity, we will see. A necessary condition, necessary means without this you cannot think about analyticity. So the necessary condition that fz be analytic in a domain is that u and v satisfy CR equations in D. So the CR equations are must. These are necessary conditions. CR equations must be satisfied. Then only if the CR equations are not satisfied, you can straight away say that the function is not analytic. Yeah. So the CR equations are must, necessary. Yeah, these are the equations are necessary. They must be satisfied for analyticity, but not sufficient. They are not sufficient. The CR equations may be satisfied, but the function is not analytic. That can happen. So they will help you. If they are not satisfied, then you will say that, oh, this function is not analytic, right? Moreover, if the partial derivatives appearing in CR equations mean these first order partial derivatives, they are continuous, then the CR equations are sufficient for analyticity. So we have the sufficient condition also. The necessary is just these, these CR equations must be satisfied. But if these derivatives, the first order derivatives, if they are if they are continuous, then this is sufficient for analyticity. Then you will say that the function is analytic. Is that clear? This necessary and sufficient conditions. Yes. Any doubt here in understanding this result, this theorem? Fine.
Hello, sir, am I audible? Hello. Hello.
Okay.
Yes, sir. Yes, sir.
Yeah.
My mic was not working.
Okay, so it's clear, right?
Yes, sir.
Okay, so we'll go at least a sketch of the proof for necessary conditions, because for this sufficient part, it has a relatively lengthy proof and more involved, where probably difficult to do in this course. But at least the first part we will get the idea that why these are necessary. So assume this fz is analytic, right? And then we will show that if fz is analytic, these CR equations will be satisfied for sure. So if fz is analytic in D, that means f prime exists at any point z in D. If f prime exists, that means this limit exists. And this limit we are just writing in terms of x and y. So z plus delta z means x plus delta x, y plus delta y. Here also x plus delta x, y plus delta y. And then we have the minus fz as uxy plus I vxy, right? So all these we have converted into x and y form. So wherever delta z is delta x plus delta y, whereas z is there x plus iy and so on. So since this f prime z exists, the right hand side limit should be the same along all the path, right? If this limit exists because function is differentiable, that means this limit exists. Whatever path you take, it should be same along any path which approaches your delta z to 0. Well, so we will take two different paths. You can see in the figure here. So P path. So here we have z plus delta z and here we have this z. So we are approaching from z plus delta z to this z, right? By making this delta z to 0. Along two different paths. One is this along P. We will first move along the y-axis and then along x-axis. In the second path Q, we will first move along the x-axis and then we will go down on y-axis. So these are the two different paths and let's see what happens. But the limit should be same because if limit exists, it should be same along all axes. So along P, so if we choose this path P, what will happen? There delta y approaches to 0 and then delta x approaches to 0. So let's do that. First delta y approaches to 0. So you can set delta y to 0 and then delta x to 0. Along Q, delta x to 0 first and then delta y to 0. Yeah, that is the difference between the two paths. So along path P, delta y to 0 and then we will see delta x to 0. So delta y is straightforward. We can make it 0 because at this stage delta x is not 0, that we will set now. So we have set delta y to 0 and now we will do with delta x. So here, what is this? Now this limit here when delta x to 0, this is ux, right? You can see this is
Yes, sir.
vy. This you can see. Yeah, please. So since this f prime z exists, now this ux plus iy, this has the existence, right? Fine. Now
So ux is the partial derivative of u.
it's a partial u. It's a partial
Okay.
v.
Yes.
We go along path q. That means delta x first 0 and delta y. So again this f prime z will be equal to vy minus iuy. The above two limits must be equal. This must be equal to this one because f prime z exists. And from there you will get those CR equations that ux must be equal to vy and vx must be equal to uy. And that is exactly the CR equations. So these are must. If the function is analytic, these equations will satisfy. So if these equations are not satisfied, that means the fz is not analytic. Or in fact, not only analytic, it is not differentiable. Fine, because we have proved this for the differentiability indeed, nothing to do with the analyticity. The function will not be differentiable even. So forget about analyticity. Yeah.
Sir, what
Can
is
you show the previous slide?
One more back here.
No, sir. No, sir.
Okay, the last slide
Yes,
which
sir.
we covered. Yeah.
Sir, why is there minus iota uy?
Here, this one.
Yes, sir.
So there is a I, there is a I.
Multiplying.
Correct.
Okay.
So therefore this minus I will appear here.
Okay, sir. I didn't see that.
Yeah.
So, why, like, what would be the actual proof of this? Like, this is just the sketch of the proof, so it appears to cover every aspect. So, why are we not calling it the actual proof?
Well, I mean, sketch in the sense, first of all, that this is only sufficient. Yeah, we have proved only the necessary condition, right?
Yes.
Here we are not getting exactly, because that is more involved also, that how to get back to the sufficient one. And the second point is, here itself there are something missing. Like, see, we have just said this, that this is ux. Did I go through in detail that this ux will exist?
No,
I mean,
sir.
well, that f prime z exists, that we know. That is the assumption. And then the right hand side we have something like this, and then we have considered, okay, our partial derivative of ux will exist. Well, it is not too bad, because see, if this left hand side exists, the right hand side should have the existence. That's for this exists, right? So,
Yes.
and then you have the real and the complex part, so each separately must exist, correct? So therefore
Since they're different, like one
yeah,
is having iota and the other is the real
correct,
term. So,
exactly.
sir, shouldn't they be separately differentiable? Shouldn't this imply that they are separately differentiable also?
That's what we have written. Yeah, ux and vx, they should be separately differentiable. Otherwise, this limit will not exist if one of them does not exist. If
True.
one of them does not exist, for instance, then f prime z will not exist. True.
Yes, sir.
So there will be no cancellation or something, because you have a real part, you have a complex part. So therefore it is, yeah, absolutely, you said it is quite I mean, complete proof. It's not just a sketch, because we have not made many assumptions or anything here to prove this. Yeah. So
Yes.
this necessary part is clear, but sufficient we will not touch here, because that is too much involved. So just a quick overview that these CR equations in polar form also useful, because sometimes the function is given in polar form. So instead of converting everything to the Cartesian one, we can also try with the polar form itself. So for polar form, you need u with respect to r, right? R and theta. So you compute del u over del r by the chain rule, and I will just skip here, because the simple chain rule, and then you substitute all these desired values here, del x over del r and del y over del r, and then you just multiply 1 over r and divide by 1 over, by r here, and then you will see that this is nothing but 1 over r, and this is del v over del theta. So once you compute del v over del theta, you will realize that this is exactly this one. So the one equation will be del u over del r is equal to 1 over r del v over del theta. And similarly, by the chain rule, again the same thing, you will get del v over del r is equal to minus 1 over r del u over del theta. So these are in polar form. These are in polar form. If u and v are given in polar form, or you convert into the polar form, then these will be your CR equations. Note, if the existence of the derivative is known, then the following formula can be used for its evaluation. If the derivative existence is known, then ux plus iv, yeah, we have seen before, right, that f prime z was ux plus ivx or vy minus iu, CR equations, right? From here we derived. So if we know that the f prime is exists, you just need to get ux and vx and put in this form, you have f prime z.
Show the previous slide once again. Yes.
This one?
Yes, sir. Now it's okay.
It's okay?
Yes, sir.
Okay. So this is just a remark that if you know that f prime exists, then you can simply ux and vx or put in this form, or compute vy on ui, put it in this form. Your fz is ready, f prime z. The CR equations are necessary, right, for f to be differentiable at a point or analytic at a point. If they are not satisfied, then fz does not exist at that point. Is that clear, this note too? Because this is what we derived there. Assuming that f prime exists, we got those CR equations. So if f prime exists, CR equations must be satisfied. If the CR equations are not satisfied, then f prime z does not exist at that point. That is clear. If the CR equations hold at a point z naught, then f may or may not be differentiable at z naught. True? If CR equations hold, because these are necessary conditions. CR equations hold, but f may or may not be differentiable at z naught. Clear?
Yes, sir.
Very good. So what we have learned, this is the differentiability. How to?
Excuse me, sir.
Yeah.
Sir, can you explain the previous one? If
No.
CR equation at point z naught, then f may or may not be differentiable at z naught.
Yeah. So if CR equations hold at a point, because the CR equations are not sufficient conditions, right? So CR equations holds, the function may or may not be differentiable. We don't know anything. We have not proved anything. That sufficient condition was something different, where continuity of those partial derivatives also play a role. So we have just proved that if f prime z exists, then CR equations must be satisfied. So how we can use this result? If CR equations are not satisfied, for example, then you can say that the function is not differentiable. But if CR equations hold, then f may or may not be differentiable.
So then how can we directly use the results in note 1? Like if ux and vx,
No.
vy and...
Yeah, here we have it. If the existence is known, if the existence of the derivative is known, if you know that
Yes.
this function is differentiable, the derivative will exist, then you can directly find out the derivative using this.
Yes, I did not notice that. Okay.
Yeah, okay?
Yes, sir.
Okay, fine. Is this point clear now? The CR equations and they may not be differentiable? Because
Yes,
necessary, yeah, necessary conditions does not imply that the result will follow. These are must. So once they are there, then you can think about differentiability. If they are not satisfied, forget it. That is not differentiable. So we have seen that if fz is said to be analytic at z naught, if there exists a neighborhood at all points of it, f prime z exists. So there is a slight difference between analyticity and differentiability. And a necessary condition to be analytic or in a domain is that you must satisfy this in the whole domain. That is the necessary condition. Well, so in this now in continuation, we will learn analytic functions, harmonic functions, and then construction of analytic function. That is also important. So we will continue with this. So little more and then we will close. So CR equations, you remember we have learned already that these are called the CR equations, and CR equations are necessary for f to be differentiable. And if they are not satisfied, fz does not exist at that point. If CR equations hold, then f may or may not be differentiable at that point. Just now we have again repeated here, nothing else. Well, so for instance, this one, now get back to this one. You know the result here that this z conjugate is nowhere differentiable, right? Let's do with the CR equations. So CR equations, we need u is x, and then you have minus y with v, because you can write this z x minus iy, right? Okay, ux is 1, uy, vx, vy. What do you see? The CR equations do not hold at any point. Ux, vy. Ux, vy are never equal, right? And neither, okay, at least the ux is not equal to uy, right? So CR equations do not hold at any point, isn't it? At any point they do not hold. Then you don't need to say to check anything. You don't have to go to that approach which we have followed, that two different paths and so on. You just say that f is nowhere differentiable. F is not differentiable at any point. Is that clear?
Yes.
Yes, sir.
Because CR equations do not hold at any point, whatever domain you take, the whole complex axis, whole complex plane, but it is not differentiable. Z real Z, that means x plus iy, and the real Z is x. So our function is x square plus ixy. Uxy is x square, vxy is xy, ux you compute, uy you compute, and vy. The CR equations, ux is equal to vy, vx is equal to minus uy. CR equations do not hold at any point except z equal to 0. Correct? So see, at z equal to ux is equal to uy. So at x equal to 0, they satisfy. The second equation, the other equation also at xy equal to 0, they will satisfy. So CR equations hold only at x equal to 0. But do they hold anywhere else? Because if your x is not 0, they x and 2x will never be equal to 0. Correct? So CR equations hold only at a point, only at one point. So that what can we conclude out of this? That the function may be differentiable at z equal to 0, right? May be differentiable at z equal to 0, but nowhere else, right? It cannot be differentiable any other point. Can we say something about analyticity at z0? Anyone? Can we conclude analyticity from
So it may be analytic at
it cannot be analytic at z
So it
equal to
cannot
0
be.
also. That is clear.
It cannot be analytic since the neighborhood is not holding
Yeah,
the.
exactly. Because at z, if at all it is differentiable, we don't know even differentiability at z equal to 0. But if it is differentiable also at z equal to 0, does not matter. It is nowhere analytic. It is not analytic at z equal to 0 also, right? So f is not differentiable at z if z is not equal to 0. Nowhere analytic. It may have derivative at z equal to 0, which we will check, and it has indeed 0 derivative. The value at 0 is 0. So the function is differentiable at z equal to 0, but nowhere else. But that nowhere else, then definitely it is not analytic anywhere, including 0. Fine, is that clear? Because this is important example for clarity. Fine, shall we go?
yes.
Okay. Similar conclusion you can draw from here also. Fz is equal to mod z square. So uxy and vxy, you separate it, ux and vy, vy, ux. Again, the CR equations are satisfied only at z equal to 0. Again, the function is nowhere analytic, and a function is but may have a derivative at z equal to 0, which we can check, and it has again a derivative. So similar example, similar conclusion, which we have already seen in the previous example. Correct? Fz is equal to mod z square root xy. Here v is 0, u is this. You calculate ux at 0. So let's just focus on 0 point. So the ux is 0, uy is 0. You should know now how to get this. This is simple calculation. So vx is also 0 and vy is also 0. So at 0, if we talk about, the CR equations are satisfied at 0 point, because everything is 0, and then they are satisfied. So what will happen now? Let's check the derivative at z equal to 0. So the derivative in this case, if you choose y is equal to mx, you will realize that it depends on path. So f prime 0 does not exist. So what is different in this case? In this example, the CR equations are satisfied at 0. The function is not differentiable, right? Because that is a necessary condition. In earlier two examples, CR equations were satisfied. The function was also differentiable at that point. But in this case, CR equations are satisfied, but function is not differentiable. Is that fine? Is that clear? Yeah, please.
So you are, I think so that CR
Yes, sir.
equations are satisfied, then the function is differentiable.
No, CR equations are satisfied. Function may be differentiable, may not be differentiable. And in the first two example, the CR equations were not were satisfied. The function was differentiable. In this example, the CR equations are satisfied again, but function is not differentiable. So we cannot say anything about differentiability if
But if
CR equations are satisfied.
if they are not satisfied, then it won't be differentiable.
Yes, if CR equations are not satisfied, then for sure you can say that function cannot be differentiable at that point. True?
Sir, if function is differentiable at a point, then we can say that CR equation will be will hold true at that point.
Yeah, if the function is differentiable at a point, then definitely CR equations will satisfy.
Okay, sir.
Yeah. Fine. So you go through again, because this analyticity is, and then you should have a clear view about the relation with the CR equations and all. So this you go through again, whatever your queries are there, you please get back.
Excuse me, sir.
Yeah.
In analyticity about a point, that at that point it should be also differentiable.
Yeah, analytic. If the function is analytic, definitely
About
it
a
has to be
point, sir.
differentiable at a point. Yeah. If the function is differentiable at a point, it has to be not only differentiable at that point, it should be differentiable in the neighborhood also.
Okay, then only it is analytic about that
right.
point.
Yes. So analyticity is little more. You don't need just differentiability at that point, but also in the neighborhood.
So we can say that if differentiable is continuous, then we can say that it is analytic function.
If those are continuous, then along with CR equations, then differentiability follows. Well, this analyticity follows, right?
Sorry, sir, I didn't hear. Your voice was breaking.
What I said, the sufficient condition is CR equations must be satisfied plus. Plus means you need something more. What more? Those derivatives which are appearing there, first order derivatives, they must be also continuous.
Yes, sir, same I was.
Yeah, naturally, that is sufficient. That is more than what you need. Fine?
Yes, sir.
Okay, very good. So you go through again, because that was very critical and we have finished that up to analyticity. So you just have your queries in this analyticity and all we will discuss. Next week we will start with the harmonic function. Fine?
Excuse me, sir.
Yeah.
Sir, I have doubt in previous class slides, sir.
Which can you just because I have a meeting at 10 now. Can you just write to me through email?
Okay, sir.
Quickly, yeah, I'll try to respond you there. Otherwise, in the next class, if I feel that it is important for everyone, I will explain in the next class. Otherwise, I will respond to you. Fine?
Yeah, okay.
Okay, good. Fine. Okay, nice.
Thank you, sir.
Yeah,
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Have a good day.
Thank you, sir.